Right, hello everybody and welcome to this week's video. This is a slightly less a slightly less massive video. Um, we're solving the Gaussian integral. Yeah, there's not much else to say. Well, what is the Gaussian integral? Well, it's this integral from minus infinity to infinity of e to the minus x. I guess Gaussian integral. Regardless, this is our integral. What does this look like on a graph? Well, we have e to the minus x squared, and it's going to look like that. That is a slightly better drawing. And we want to find this area the whole way all the way to minus infinity and to plus infinity. So that is our aim. Now this has no elementary antiderivative in terms of any functions that we have, so we've got to kind of use a trick, and the whole trick revolves around working with I squared. So what is I squared? Well, it's going to be 2 of that. That's infinity to infinity of e to the minus x squared dx times itself. Infinity to infinity of e to the minus x squared dx again. We can just swap this out for a dummy variable because that's allowed. So then this is going to be e to the minus x squared dx times the integral from minus infinity to infinity of e to the minus y squared dy. Now, keen viewers, and also if you've watched my channel, you probably are aware of how to do this already. So maybe this will expand my horizons in terms of audience, but this is not particularly masked away from the fact that we are attempting to turn this into 2D, a two-dimensional integral over the xy plane, and these integrals are completely independent, so they satisfy the condition for Fubini's theorem, which allows you to combine them. So we get simply then that this is the double integral. I'm not going to continue writing minus infinity to infinity. I'm going to write over r, because it is over r. I guess you should really write. No, you can just write r. R squared. R of e to the minus x squared e to the minus y squared dx dy. This is allowed. And of course we can use our we can use our indices rules. This is x squared plus y squared. Yet again, keen viewers may be now interested in goodness me, this is really not taking long enough. Keen viewers may be interested in something we have up here, which is x squared plus y squared. And I'm sure you're aware of the identities of polar coordinates, those being that if we take x to equal r cos theta and y to equal r sine theta, then x squared plus y squared is equal to r squared cos squared theta plus sine squared theta. That's just 1, so it's r squared. Well, isn't that wonderful? We have now simplified it into a polar Gaussian. Now there's a problem, which is we know that because we're working with a double integral, we need to use our Jacobians. So we're going to do a Jacobian, I think is probably correct. A Jacobian determinant. That being, we have our dx dy. This is equal to some determinant of our Jacobian times dr d theta. So let's find out what J is. Well, we're going to end up with our partial derivatives here. So we'll have dx, dr, dx, d theta, and then dy, dr, dy. Oh no, it's sorry. How to rub there? Erase dy, dr, dy theta. This is my glorious, lovely, beautiful matrix. Now, what do I do here? Well, it's going to simplify down even further. Let's look at our bits and bobs. Well, what's dx dr is just going to be cos theta. Dx d theta is just going to be minus r sine theta. Obviously, derivative of cos theta is minus sine, and then this is going to become plus sine because obviously we get rid of that. And then in the bottom right, it's going to be r cos theta because derivative of sine is cos, and that leaves us with the following matrix: cos theta minus r sine theta, and r cos theta. So now all that's left is to take the determinant of our Jacobian, which is going to be cross and cross, so cos theta, in fact it's going to be r cos squared theta minus r sine minus r sine squared theta, so plus r sine squared theta. You may see where this is going, which is going to be r cos squared theta plus sine squared theta, which is simply r. So we have a useful differential area element transform, which is that dy dx then becomes r dr d theta. Anyone who studied polar coordinates in school, you will see that when you square the expression. So we can do things with our I squared now, which is this. I'll make that clear, that is still I squared. The last thing we need to do is boundaries. Importantly, for coordinates, we have that r is in the following boundary, whereas theta is between 0 and 2 pi in a closed set. So now we end up with two integrals, and one will be dr, one will be d theta. So I can no longer write over r. So you have 0 to 2 pi even, and then 0 to infinity, and that will be e to the minus r squared from above, and then r dr d theta. Cool, I'm happy. And now we can work backwards from earlier. We split this into two integrals, 0 to 2 pi d theta times 0 to infinity e to the minus r squared. I put r there, r e to the minus r squared. Now we have something that has an elementary antiderivative, which is wonderful. Dr. Of course, this is simply going to evaluate 2 pi minus 0, which is 2 pi. So now we have 2 pi times 0 to infinity r e to the minus r squared dr. Of course, yeah, that's trivial. And now we need to work out how to actually come up with a solution to this. This factor of r gives us the perfect sort of integrand. So we're going to do a u sub. U equals r squared, du equals 2r dr, so dr equals du over 2, that's r dr equals d over 2. Of course, whoa, that's going to go in there, and then it is simply I squared equal to pi, because that 2 comes in, from 0 to infinity of e to the minus u du, which is pi times minus e to the minus u from 0 to infinity. Now we can just take limits here. This is pi limit as u goes to infinity of minus e to the minus u minus minus 1, because minus 1, because anything 0 is 1, and then minus that minus 1. Now, if you were to look at a graph of this, I could pull one up in Desmos. I'm not sure if I'll be able to. What I'll do is I'll pull it up in Desmos. What is quant? It's changed my search engine. I did not ask for that. If I pull up the graphing calculator in Desmos, and very swiftly graph it so that we can get a nice u minus x, I'll say. Well, it becomes fairly obvious here what this is going to limit to. That is our graph. So yeah, fairly obviously, this is then going to limit to 0. You can see there it pretty much stays along 0 for most of its existence. And so we are left with this being equal to pi times 0 minus 1. Well, it is pi. So I squared is pi, therefore I is root pi. And so we can conclude that the integral from minus infinity to infinity of e to the minus x squared dx is equal to square root of pi. Yeah, so this is a really cool trick. It's good fun. The only hard bit is the Jacobian, but even this is a lot of big letters that aren't really doing anything. It's good fun to solve, and it's really cool how it becomes root pi, and you can start to see where it's not surprising that when you go into polar coordinates you end up with a pi somewhere. But yeah, I don't know what else to say. This is a really important integral. Often in quantum mechanics we end up with an integral of e to the power of another integral. Sometimes that may be simplified to something Gaussian-y. Often in statistics, of course, the bell curve is a scaled version. Well, you scale the version of the bell curve so that the area underneath is 1. And so that the standard deviation is the standard deviation and the mean is the mean. To which extent you get the probability density function for the bell curve, for the normal distribution rather, of course that being this, and so those this tends to be very useful for budding statisticians before you ascend to the realm of R and Python. But yeah, it's cool, and hopefully I gave a fairly clear explanation as to how it's solved. And now every time you see the cake video, you'll understand exactly what's going on. Anyway, thank you very much for this slightly shorter video. Thank you for watching. And next week I will be sure to be back. I'm thinking of, I don't know, should I say? It won't be that bad. We might look a bit more into operators. I kind of just pulled the momentum operator out of nothing last week, and I thought it might be good to go over and explain where that comes from. Oh, before I forget, I'm going to put this in a box, and then I will wish you all a lovely week. It's a terribly placed box. Can that be rectified? It can. There we go. Right. With that, thank you very much, and I will see you next week. Goodbye.